Okay, so it's 10:30, so we'll go ahead and start. So far there are 8 of you. In this class, actually there are 20 students, 10 masters and 10 PhD. So far there's 8. I'll go ahead and start. So the class is scheduled from 10:30 to 12:30, which is a 2-hour class. And in the evening, you can make use of a Minitab survey, whatever I'm teaching you today, as well as you can also go through whatever Dr. Anik has taught you 2 weeks ago. Okay, so Dr. Anik touched on DOE, Design of Engineering, where he covered factorial design and also fractional factorial design. So, and then Dr. Abang did data collection, analysis and processing. So today I will cover statistical methods, which comprises of some basic statistical methods that you can do in Excel, as well as I will also give you an overview of Taguchi method. Okay, so all this will take about 2 hours. At about 11:30 we'll have a bio break, a mini break, and then we continue on to 12:30. So in the evening, you can make use of the time, because it's a whole day class. You can make use of the time to get familiar with Minitab. Okay, so I've just found out that in Minitab, apparently the trial version you can't use all the examples. So so perhaps you should talk to your supervisor. If you really want to use Minitab, then you need to talk to your supervisor to purchase it. Okay. Alternatively, I have my version, but my version is a bit old. It's version 14. The latest version is version 19. Okay, so depending on your research and your needs, discuss with your supervisor and co-supervisors. If you really need to use it in your research, then go ahead and get the software. Okay. Otherwise, if you ask me, Excel is good enough for basic research. If you want to go deep into statistical methods, then you can go ahead and get your supervisors to purchase Minitab or any other statistical software. All right. So we'll go into the slides. Okay, so my slides will be uploaded after the class. So I've had some issues with my network. So I'll upload after the class. Okay. All right. So I'll share my screen now. Okay, share content. Okay, can you see my screen, students?
Yes,
hello?
Doctor.
Can? Okay.
Yes, yes.
Yes, ma'am, we can
Okay.
see.
All right. So my name is Susi from IMEN. So all of you are also from IMEN. I'm from the Photonics lab. Okay. So I think a few of you have taken my class before this, Applied Nanoelectronics and also Fundamental of Nanoelectronics. So these are my brief background. I did my degree, my master's and also my PhD all in UKM. So in between I worked with Intel for about 3.5 years, almost 4 years. And currently I have 6 master students who have been completed either as main supervisor or as co-supervisor. 18 PhD, and currently I have 4 PhD students ongoing and 3 master students ongoing. So in terms of publication, more than 180 Scopus and ISI journals and proceedings. So currently I'm working in plasmonics or quantum electronics, okay, and also in nanophotonics, and these are some of my previous research projects, okay. So my expertise is in nanophotonics, which is mainly in surface plasmon resonant based nanosensors, optical fiber based and also waveguide based. I also have expertise in fabrication and characterization of optoelectronic devices using spin-on diffusion technique. Also FAM-based numerical analysis. This is for Silvaco, Lumerical and also COMSOL. So COMSOL is mostly on electrochemical effects, all right, not on the device per se, but on the electrochemical effect. Also in statistical optimization, fractional factorial design, and also Taguchi method. So I'm seeking for masters and PhD students for plasmonic based projects. So if you have any contacts who are interested, please ask them to drop me an email at susi@ukm.edu.my. Can you guys see my pointer?
Yes, ma'am.
Okay, all right. So so feel free to stop me if you don't understand any part of the lecture. All right. Since there are, I think, 2 or 3 foreign students in this group, so I'm using English. But if you do not understand any English terms and you want me to translate, please stop me. Let me know, and I can explain to you in BM if needed. Okay? Faham semua? Okay?
Okay.
All right. Okay. So basically, I'll cover introduction, overview of statistical methods. So this is actually a recap of what Dr. Abang presented, but I will zoom in a little further into the statistical part. And then we'll review some case studies of DOE and also Taguchi method. Okay. So at the end of this lecture, you're supposed to be able to effectively process experimental data, identify different quantitative data categories. So this is in comparison with qualitative data, which is normally used in social sciences. So since all of you are in IMEN, I presume that all of you will be doing experimental work, and which involves quantitative data. Okay. And I hope by the end of this lecture, you can understand basic statistical tests that can be used for data processing during research experiments, and also to comprehend design of experiments mainly on Taguchi method. Okay. The introduction. Okay, so this is a news article. So it says that 2020 is a new decade of opportunity for statisticians. I'm not asking you to change your job scope, but I'm just telling you that statisticians are in demand. They are ranked as the #1 best business job, #6 among the top 100 best jobs. Okay, and if you have looked at the rankings in the previous years, so it's because of this IR 4.0 and the amount of data that is available now. So statisticians are really in demand. Okay, so if you can have the skill of being good in statistics, so it is an added advantage. It's definitely an added skill for you. Okay. So you have all this data from your research. Okay, so they say that a picture or a graph or an image is worth 1,000 words. Okay, so you take that data and put it into a figure, into a graph, or into a histogram and so forth. So why is an image worth 1,000 words? Because 90% of the information transmitted to the brain is visual. So you put a picture, people can absorb more information rather than putting in text or just raw data. Okay, and visuals are processed 60,000 times faster in the brain than text. 80% of people remember what they see, all right? And 92% of all human communication is non-verbal, doesn't involve talking. So it's more to images, figures, and so forth. So for your defense proposal, which will happen in a few months' time, so as much as possible, try to use more images, explain your methodology, your problem statements, use more figures, and try to get the message across using figures and images. Okay. So this is, okay, you look at this image, it says COVID's staggering impact on global education. This data was extracted in February until March, and you can see the increasing trend, the number of learners impacted by national school closures worldwide. So just a simple histogram data, but you can see the impact is 1.38 billion. So the message gets across. So this is when COVID started to hit us, and you can see the impact to billions of school students, including tertiary education levels, including you and I as well, okay, the lecturer and the student as well. So how much it has impacted all of us. So this is where statistics is useful to portray or give information. Even in the daily COVID-19 updates by the Ministry of Health, you can see various types of statistical data are put up in the form of images. You look at the image, you understand which district has got the highest number and so forth. So translating data into images, graphs, which are very meaningful for people to understand. So for research students, this is very important for you for your publications as much as possible. Use the data and translate it into understandable or interesting figures and images so that you can capture your reviewers or your examiners' attention. Okay. So in terms of research, if you look, this is the internal and external examiner report. So item number 10 says that the quantitative and statistical analysis. So I'm not saying that you must use statistical analysis, but you must have some sort of quantitative analysis in your master's or your PhD work. So it asks the examiner whether is this quantitative or statistical approach, is it thorough and also extensive, right? Analisis kuantitatif atau statistiknya menyeluruh. Jadi data yang diperolehi perlu digunakan untuk menghasilkan graf ataupun histogram dan sebagainya yang dapat menyampaikan maklumat daripada raw data yang kamu perolehi daripada masters atau PhD. Dan tugas pemeriksa luar atau pemeriksa dalam adalah untuk menyemak sama ada data yang awak perolehi itu betul-betul bermakna atau tidak. Okay. So you have interpretation as well. All right, else than using quantitative and statistical methods, you also need to interpret. Data itu mesti diinterpretasi dengan betul dan tepat. Okay. Okay, so this is the overview of the statistical methods, and you'll notice that some of it is overlapping with Dr. Abang's slides, so it's just like a refresher for you. So I'll just run through this quite fast. Okay, so you have your problem definition, problem statement, okay, and then you decide on what experiment you want to do, simulation based, experimental based, both, and then you construct your experiment based on design of experiment or so forth, and then you start gathering your data, and then you need to do statistical analysis, and then you interpret the results whether your problem or your hypothesis is correct or wrong, or you want to define and inform people whether your hypothesis is correct or wrong, or whether the problem statement that you gave, was it solved because of your experimental work. All right, so you interpret and you report out. In terms of data collection, just sharing some 10 important steps. So you have to think about the types of data. So most of you are in your semester 1 to semester 3. So for master student, if you're already in semester 3, I think more or less you're already clear on what you need to collect. But if you're in semester 1, you need to be very clear about what type of data you need to collect before the semester ends. If you're still unsure, please go see your supervisor, your co-supervisor, and clarify what data do you need to collect. All right, at this point of time, you should already know what are the data that you need to collect, and the types of data you'll be collecting, where you'll be getting the data, and make sure the data collection form or the template is clear and easy to use. Okay, I cannot stress how important this step is. Make a duplication copy of the data file and keep it in a separate location. So more often than not, we tend to save everything into our laptops without having backups. So my suggestion to you is you have an external hard disk drive, and you schedule a weekly backup of your data, so that in case your laptop gets corrupted, your data is still safe inside your external hard disk drive. Please do this early. Don't fall into the trap at the moment that you want to type your thesis or you want to submit a paper and you find that your file is corrupted and everything is lost. So you have to start back everything from scratch. So this step is very important. Whether you're a master's or PhD student, duplication copy of your data file. And next is do not rely solely on other people to collect or transfer data. So sometimes in your research group, there may be 2 or 3 people working on the same project. And yes, we work with each other, but it's good that you collect your own data rather than asking someone else to collect it for you. Okay. And plan a schedule, when, where, how. So now you know in IMEN we have a schedule of when the labs are open. So it is a bit difficult because you can't go in as often as you want to, but at the same time, if you have proper scheduling, you can plan how exactly and when you're going to collect your data. Cultivate possible resources for your subject and pool, different experimentation techniques, follow up on experiments that have been missed, and please avoid the habit of skipping. If you're a master student and if you're aiming for graduate on time, so within 4 semesters, and if you're a PhD student, within 6 semesters, if you're aiming for graduate on time. So it is a very short time actually. You don't have much time. Taking into account, sometimes your equipment may not be up all the time. It can go, some problems may happen to it. So taking into account all this, so as much as possible, try to avoid skipping. When you're scheduled to do your experiments, do not skip it. Okay. And it's also good to practice this. Do not discard the original data, because it's good to have this logbook where you document every day what you did. All right, so for today, you attended class, and then after this, suppose you go to the lab and do some experiments. Write it down. What did you do? What data did you collect? And it's very good to maintain these logbooks throughout your research experience. So you know why? Because sometimes maybe 1 or 2 or 3 semesters down the road, you find that you may need to repeat something that you've already done before. So having the logbook helps you, because then you may not need to repeat it again because you already have the data. And so it helps you to keep track of what you have done and what you have not done and how to plan for the next step. Okay. And the last but not least is following all the above 10 commands. So these are the 10 important steps in data collection. Okay, so just a recap of what Dr. Abang presented last week. Okay, now we move on to statistical analysis. So I sent out the survey form, and I found that since this class involves both master student and also PhD students, so the master students may not have much exposure or knowledge in statistical software, so they may just need to use basic Excel statistical methods. So I will cover both. I will cover how to use Excel for simple statistical analysis, and for PhD students who are interested in more complex statistical analysis like design of experiment, that was covered by Dr. Anik, and I'll cover Taguchi method. Okay, so I try to fit both of your needs, the new master students and also the advanced PhD students. Okay, so but having said that, I cannot cover everything inside the Taguchi method, because it's actually a 3 days course. Okay, it's a 3 days course. I've compressed it into 30 minutes. Okay. So if you need more information, so you can join the full-fledged course, which is for 3 days. Okay. Okay. Qualitative data, just an overview. This is a recap of what Dr. Abang has already taught you. So it's concerned with non-measurable aspects of data. So it's non-numerical. So text, audio, video, and image data. I believe that all of you are doing quantitative, unless you are involved, portion of your research involves social science, then you'll have some qualitative data. Okay, so basically in qualitative, you have language-oriented, descriptive and interpretive, and also theory-building research approaches. And quantitative, you have deductive, that means you infer or you refer from general principles, which is from you test existing theory, or we call it top-down approach. There's also inductive. That means from facts to hypothesis to conclusions, and you generate new theory. So this is a bottom-up approach compared to deductive. All right, and model building. You can describe a system or a process using mathematical language. Okay, so this is recap. Okay, Dr. Abang already covered this, but just a gentle recap. Quantitative data, you also call it numerical or statistical data. So the most common is mean, standard deviation, and frequency deviation. In Malay, it's called purata, sisihan piawai, and sisihan frequency. Higher level statistical analysis. Do you need to do this? It depends. It depends on what kind of experimental work are you doing. It depends on the needs that your supervisor needs according to the grant requirements. So if there's no need, you don't need to go into this higher level statistical analysis. Okay, you can just use normal histogram and also graph and regression lines to answer your research questions. Okay, so there is t-test, factor analysis, regression, and also ANOVA, analysis of variance. Okay, so summarizing data, which are a bunch of values with one or more variables. So a variable is something that has many different values. It can be numbers or it can be names depending on the variable. It can be numerical, for example, weight. You can count, for example, the number of injuries. It can be ordinal, competitive levels, for example, numbers or names, or it can be nominal, like gender, female or male, right? Nominal values. Okay. All right, when values are numbers, we visualize the distribution of all values in stem and leaf plots or in frequency histogram. And you can also use normal probability plots to visualize how well the values fit a normal distribution. When values are names, we visualize the frequency of each value with a pie chart or just a list of values and frequencies. Okay. So this is a simple classification of statistical method. So basically you have descriptive methods and you also have inferential methods. So if you're dealing with a descriptive method, you can have one variable. When you have one variable, then you can look at the shape, the center, the spread, and the relative position. If it's bivariate, there's two variables, you can look at correlation and also regression or prediction. And if it's multivariate, you can use multiple regression. Okay. And for inferential methods, you can have parametric statistics applied to means. There are two groups, or also analysis of ANOVA.
Doctor,
Hi, yes.
Sorry to interrupt. Can I ask a question?
Yes, sure.
The univariant, bivariant, and multivariant is the variances is difference, is it? Can you explain what is the univariant, bivariant, multivariant?
Okay, so this is like if you have only one parameter, right? Like one parameter only, you only have to look at, for example, surface roughness only, surface roughness of gold nanorods, for example. You only need to look at that output, one variable. Okay, or another example can be, these are mostly histogram based, right? They are mostly histogram based. Like you want to see how, yeah, like roughness of gold nanorods, right? So you want to see if you change these parameters, what will be the roughness of the gold nanorods, or if you change the temperature, you change the material and so forth. Okay, so that is single variable. Bivariable means normally it's an XY graph. Okay, you have an X and a Y. For example, temperature versus thickness. Okay, so you want to see what is the relation between those two variables, X and Y. That's when you have an equation, Y equals to mx plus c, right? So it's bivariate. That's, you are trying to find the relationship between two variables. Okay. And multivariate is when you have more than two. So you want to look at the effect of temperature on thickness, and also on roughness. All right. So that is multivariable. So you have more than 2 parameters or variables involved. Okay.
So, Doctor, can I say the x1, x2 is the variables and y is the output? So we're not considering
Yes.
the output. We're looking at the x1, x2, x3.
Yes.
All right. Thank you.
Actually, you're trying to look at variables. You're like trying to look at the relationship between the input and also the output.
All right.
Yeah, you're trying to look at the relationship between the input and the output. So that means here you're only looking at normally this is histogram based, right? It's normally a histogram. You want to look at population, or there are some examples later on. So you just want to look at the shape of the histogram. All right. And bivariate is normally in the form of XY, a normal graph. And multivariate, you may have more than one graph,
All
right?
right.
Yeah, you'll have 2, 3 XY graphs, right? The effect of several factors.
All right.
Okay. Okay. And these are some common statistical term, all right? And I think Dr. Abang has also gone through this, but I'd like to bring your attention to what is a discrete variable and also a continuous variable. I believe most of you are working on discrete variables, right? Where it involves a number and you cannot subdivide the number. But if it's a continuous variable, for example, it's income, height, and length, we consider that as a continuous variable where you cannot, it can be subdivided, and normally continuous variables are used as histogram based, right? And discrete variable are normally the ones that you have a XY plot. Okay. And you also have case, population, and sample. So these are normally used for statistical. Normally, when you have a large experiment and you look at only a small portion or sample, and you need to know all these terms. Okay. Measurement, nominal, whether it's or categorical, and ordinal, whether it's a rank, right? Low income, medium income, high income. And nominal is normally, so it's like a label, right? And you cannot mathematically manipulate them. So for example, female and male, right? And so this is categorical versus ordinal. Okay. So interval scale, so measurements on a temperature scale, the range, right? The interval. The ratio scale, for example, the length in meters. Okay, so these are common statistical terms that you always come across, not only in examples, but also in journals and your literature review. Okay. Okay, error analysis. So if you're working with equipment, so you must be aware of systematic errors which are consistent. Blunders in the measuring process when you're measuring for your voltage or for your current, and if you're supposed to get 0.4 volts or 0.6 volts and all of a sudden you get 1.5 volts, you must be aware that it's a systematic error. Something is wrong somewhere. Perhaps your current is higher because there's something short somewhere. Okay, so else than that, you also need to know about random errors, which is a natural limitation of making physical measurement. For example, when you repeat a measurement a few times, you're not going to get the same value. So that's why we have what we call the error, right? 0.5 plus minus 0.1 volts, right? You have your error. So it can be between 0.4 to 0.6. So these are random errors due to the nature. So it's a calibrated instrument, but just because of the environment of repeating the experiment, it can give some errors. All right, we call it random errors, and we have a method statistically to counter for these errors. Okay, so you just have to be aware of systematic errors. That means these are because your equipment is not set up properly. So systematic errors can be a big problem for your experiment. random errors is common, right? Any experiment that you do, you'll come across random errors. Okay. I move to the first. Okay, so those PhD students, you bear with me. These are very simple examples because I want to cater for both the master students as well. So this is a random behavior of an experimental result. So you have a measurement of a temperature of hot gas flowing through a duct. So this is a duct like a chamber. So you have temperature, the hot gas is flowing through here. If you're using CVD or a furnace, so you have hot gases flowing through the chamber. So it shows variability when measured over an hour. Okay, so this is for 1 hour, and this is the temperature measured inside the chamber. So it is a random variable. So the question is, will the temperature exceed certain extreme limits? For example, will it go below 1085 or will it go higher than 1117? If you look at the highest number is 1117. Yeah, 1117. Okay. And if will it go below 1085? So you have some raw data and then you bin them into categories such as this bin, and then you produce a histogram of the various bins, and you can see that this is a normal plot, a Gaussian plot. Okay, so there is an Excel sheet for this. Okay, so this is example 1. So this was all the collected data. Okay, all right, this was all the collected data of the chamber temperature. So you take this data and then you can bin them into bins, right? How many 1089, how many 1092, and then you bin them into different categories. And then you can use this and you can create a simple histogram. So I believe that all of you are familiar with Excel, but in my previous experience, there are students who are not familiar with Excel, but I presume that all of you are very familiar, okay, in making Excel sheets. So if you have a temperature and you have number of measurements, so you can just go to charts over here, and normally you can have an XY chart, or you can straight away go to the histogram, right? A 2D column and so forth. But this one, I'm going to just use it as a XY, and then I'm going to change this into design. Okay. Okay, change chart type. So you can use a column. Okay. Okay. All right. So this is how you get a simple histogram chart. Okay. And you can go ahead and also label. So those who are very good in Excel, bear with me for a few minutes. So and then you have this format selection. Okay, if you go down here, you can add normally for your journals or your papers, you do not add a chart title, all right? So please don't add a chart title, all right? Because normally you will have a legend beneath here, right? To name the label, the chart, okay? And over here, you can add the vertical value, or you can also, this is for the plot area, you can also go to the you can actually label the x-axis and also the y-axis. Okay. All right, and format. This is for the value in case you need to change the value. And in case you want to put in major grid lines, or you can add the grid lines as well. And else than that, you can add the axis title. So this is the horizontal. Okay, so you can go ahead and add the temperature. Right. And can go back to design, and you can add the vertical, which is the number of measurements. All right. Number of measurements. Okay, so important things about figures is units. All right, so this is in Celsius. Okay, so make sure you have your X and Y axis labeled. You need to make sure that there are units. And if preferably do not have grid lines, all right, if you're putting it into a journal or into a book or anything, it's preferably not to have a grid lines. And make sure they are readable, all right, make sure that the font is readable. Okay, so this one is already done. I'm going to delete this. So you can also adjust, right? You can adjust the color. All right, over here you can adjust the color, you can adjust the edges, and then you can overlap with other data as well. All right, in fact, you can also change the gap width and so forth. So many things that Excel can do to customize your data into something that is visible, all right, statistically. Okay, so I'm going to go back to my slides. Okay. 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 Okay, so we stopped here. Okay. And so if you notice just now, the random variable, and this was the frequency, and it had a nice symmetric distribution. So the shape of the distribution is important because it tells you about how your variable differs with with the random variable. Okay, and B is showing a skewed to the left, and this is J-shaped, and this is a bimodal. You have two peaks, bimodal, and this is uniform. All the values are same. So when you put in a figure, doesn't matter if it's a histogram or an XY plot, what is the first thing that you should do? If you're going to describe a histogram or an XY plot, what are the things that you need to mention? Anyone? Hello?
I guess you need to understand that the distribution is normally distributed or a different other distribution in behave. Yeah.
Okay.
Then only you
Okay.
will do
So
the statistical
okay.
analysis after that.
Okay. Good, Siva. So can anyone give me a few sentences? Okay. I'm just trying to make this interactive. I don't want it to be one way. So can someone tell me a few sentences about this this figure over here, this histogram? A few sentences, maybe 3 sentences. Anyone wants to try?
Professor, do you mean about the distribution? I mean,
yes. Give me 3 sentences about this figure. Number of measurement versus temperature range in a duct. Give me 3 sentences about this image.
maybe we can say that the here temperature range is following a normal distribution with mean of around 1100 around, and it has it is actually symmetrical. It means that it's pure random, and most of the samples are considered in the middle. It means that it doesn't have any systematic error.
Very good, very good. So Who was that just now? I didn't see who was talking. Who was that just now?
This Purman, Muhammad Purman.
Oh, Purman. Okay, Purman. Okay, very good, Purman. So you're a PhD student, so you should be very well versed. So just for the benefit of the master students, so when you have a figure, the first thing that you should mention is like what Purman said. Figure 1 shows the number of measurements for various temperature ranges. All right. And Purman also said that it's a normal distribution, second sentence. Third sentence, with a mean at this range, 1100 to 1105. And you can also say that it's a normal distribution, and the fourth or the fifth sentence should actually go into the why it's high in the middle, or why it's why is it distributed in such a way. So when you have a figure, you have a histogram for all an XY graph, the first thing is you tell what is versus what. The second thing, you can talk about the shape. And then the third, you can talk about the statistical distribution, like the mean or the median or the mode, or what range is the highest. So you describe the figure that you have put into your journal or your paper, okay? And then you go into critical discussion. Why is it high here? Why is it normal? Why? You go into the critical discussion and relate it to the physics or your problem statement and so forth, okay? So I hope it's clear, especially for the master student. This is the way that you describe your figures. Okay, so we move on. Okay, so we looked at the distribution, and these are measures of central tendency. You have mean for a sample and mean for a population. So as Dr. Abang mentioned in his previous lecture, so a sample is a small portion of a population. You take a certain number of statistically significant number. You also have a median, which is the number or the range which occurs the most. And you also have, or median is the middle point, and mode is the one which occurs the most. Okay. You also have a deviation. How much is the value deviated from the mean? Okay, and this is the mean deviation. You divide by the number of samples. And you also have population standard deviation, or we call it sigma, and you also have sample standard deviation. So you don't have to memorize all these because all these are already part of Excel, okay? But you should understand what's the meaning though. So for example, variance is given by sigma squared if it's a population, and it's S squared for a sample. So for the example just now that we saw, okay, if I may go back. This example over here. So Excel has got all these, if you see here, you just put a equals to and you type the word average, it will give you the average of course you need to select the data. Okay, if you see here, this is the data which is selected. Can you all of you see my screen?
Yes,
yes?
Doctor.
Okay, so this is the average. You select all your data and you get the average value. And this is the median. Okay, the midpoint, all right, and this is the standard deviation is given by STD EV, all right, and this is the variance, and this is the mode. Okay, which number occurs the most? Okay, which is 1104, it occurs the most. Okay, so you can do this in Excel. So I go back to my slides. Okay. So, so you have got all those measures of dispersion, okay? And moving on, all right? So another method that you can use to show your data. So just now was a frequency versus the temperature range. Sometimes, in some cases, in your experiment, it is very important to normalize the y-axis, right? For example, you want to measure these are three different parameters, okay? And in order to compare them, you need to normalize the y-axis, All right, so in the case of the temperature just now, we look at the relative frequency. Okay, and it says here, what is the probability that our next measurement will be between 1105 and 1110? So you use the sample data from the population. This is the use of an empirical distribution, which was just now. So what you do is you plot the relative frequency versus the temperature. So just now was the actual number. Now is the relative frequency. What do you mean by relative frequency? Okay, let's go back to the Excel. Okay. Okay. So relative frequency just means that you take this value 1 and you divided it by the number of samples, right? 1 divided by 60, all right? And then same, 3 divided by 60, 12 divided by 60, 21 divided by 60, and so forth. So you get the normalized frequency, all right? And this is also the probability of, so the question was, what is the probability that the temperature measured will fall into this bin over here? So the answer is 0.2, right? That is the probability. Okay, so I'm just giving you some ideas. Instead of just plotting frequency or number of measurements versus the temperature, you can look into other methods of using your y-axis in terms of normalized frequency. But this is where applicable. It's not every time you do a normalized y-axis, where applicable related to your experimental work. Okay. Moving on, so this is an example of raw data. Okay, so it is just intensity versus time for 3 different experiments. So what they did was they did a normalization of all 3, where they looked at the I max minus the I mean, divided the actual measured value I minus the minimum current, I presume this is current, or the intensity, divided by I max minus I mean. So they normalize it and you are able to compare all 3. All right, so which gives the best in terms of rise time, right? So this looks like this increased intensity the fastest, right? The one SCFPA3A. So in this way, you can make some useful comparisons. If you look at this figure, it's hard to mention which one has the fastest rise time, right? So in this figure, when you normalize the y-axis, then you can make the deduction or the conclusion that this third dark green is the one with the highest rise time. So it's important to know when you can normalize your axis and report data in a meaningful way. Okay, that is the message from here. Okay. Sometimes the sample size is small, so the frequencies of individual bins are uncertain. So you need some estimates of the probabilities. It can be only approximate, and you can use mathematical functions to predict the properties of the parent population in case your sample size is small. And if you have discrete random variables, do you still remember what's discrete random variables?
Yes, doctor.
Okay, if you don't remember, you can look back in the previous slide. Okay, discrete means it's like
Yes.
1, 2, 3, 4, 5, 6, right?
Yes,
And
ma'am.
continuous means it's like a range, right? Income, height, right? It's a range. So if it's a discrete, you use probability mass function. If it's continuous, you probability density function. There's something called goodness fit to determine whether the distribution function is suitable or not. And examples of probability density functions is like Gaussian, binomial, and also Poisson. Okay, and we look at Gaussian. Okay, this is example number 2. All right, this is data collected for measurement of the mass, the weight, yeah, berat metal strip, logam, kepingan logam. So you measure 24 times with the same instrument. Okay, so these are the measurements, and this is the reproducibility of it shown in a histogram. So the value that occurred the most, what is the value that is occurred the most? It is called what?
Mode.
Mode. Yes. So mode is 8.148. It is the highest. The frequency, right, is the highest. Okay. Okay, so the bell-shaped curve denotes normal probability. So again, this figure shows the frequency versus the mass of metal sheets collected 24 times. It shows a normal probability distribution. And what is the mean? The mean is the average with a mean value of 8.148 grams, and standard deviation is 0.004 grams over here. Okay, but so the mean is the most probable value, the average. The standard deviation is the measure of the breadth of the curve. So mean is the average value, the most probable value, and this is what we call sigma, or the standard deviation, right? It's the measure of the breadth, how big is the curve. So less precise the measurement, the broader the distribution, the larger the standard deviation. All right. So you want your standard deviation to be small, not large. Okay. And the probability of finding x minus s and x plus s is 68.26. Okay. So look for x plus s and x minus s. All right. The probability of getting it is 68.26, where you are only going to get 16 out of 24 measurements will be between 8.144 grams and 8.152 grams. Okay, if you go back here, so one S is 0.004, so 8.148 plus 0.004, you get 8.152. So if you use this kind of measurement, right? If you use this kind of measurement, you measure or you report your data as the probability of finding the next measurement is 8.144, or rather 8.148 plus minus 0.004 at a confidence level of 68.26%. So it is not impressive, right? 68%. So how can you state the results differently? Okay. Okay, this is a normal distribution from Z, from 0 right until 4.0. This is what we call the confidence interval. So just now we looked at 1 sigma, plus minus 1 sigma, right? This is 1 sigma. Okay, this is 1 sigma, plus 1 sigma, and minus 1 sigma. So you say it as plus minus 1 sigma. Okay, so if you look at the confidence intervals and probabilities for 1 sigma, okay, 1 sigma, it is 0.3413 over this normal distribution curve over here. So 0.3413 for one side, but if you calculate both sides, plus and minus, you get 0.68.26 or 0.6826, and if you change it to percentage, it becomes 68.26. Is that clear? 1 sigma? Hello?
Yes.
Okay. All right. Now, what if we take our confidence interval as 2 sigma? All right. Just now we look at 1 sigma, which is over here, 1 sigma. Now we go to 2 sigma. All right. Your mean value was what just now? It was 8.148. Instead of taking 0.004, you take 2 sigma, 0.008.
Yes.
Okay, if you take 2 sigma, look at the confidence level, it's 95.44%. All right, so you report your data as 8.148 plus minus 0.008, because now you're using 2 sigma. And what is your confidence level? It is 95.44%. All right, so just imagine 68.26% versus 95.44%. So you're more convinced, or you're more you believe the data more, 95.44%. The percentage of getting it accurate is very high, 95.44%. And so forth. You have 3 sigma. Over here, 3 sigma is 99.74%. You have 3.5 sigma, 0.4998, which is at 99.96%. So anyone here from industry? Are you from any industry? Nobody's from industry. Okay. So if you're working in a multinational, or if you're from an industry, a common term is 6 sigma. All right. So you can see this is the mean, and 1 sigma gives you 68% confidence level. So 2 sigma gives you 96 confidence level. 3 sigma is 99.7. But look at 6 sigma, right? There is no probability for error, almost zero error. So in industry, they always try to aim for 6 sigma. Okay, that means when you manufacture anything in an industry, you try to make sure all your yield and your output are within 6 sigma. This is your upper limit and your lower limit. So there is very, very small value of error to occur. Okay, so if you're interested to know what is 6 sigma, right, you can go to this YouTube. I'll post it later in UCAM folio as well to understand further what is 6 sigma. Okay, so I hope it's clear to all of you what is this sigma. Okay.
Yes, doctor.
Okay.
Okay, doctor.
All right. So we move on. Okay. So in a normal distribution, 95.44% of all observations will fall within the limits of 2S. So 19 out of 20 individual measurements will be within 2S is 0.008 of the mean value, 8.148. So you report your data as 8.148 plus minus 0.008 at a 95.44 confidence level. Okay, so this is what we call confidence interval of your experiment. Okay, this is taken from a journal from IEEE Explore. So it shows that figure 8, it shows the percentage versus the crossbar size, distribution of 3 different metrics, which is the uniqueness, the uniformity, and also the bit aliasing for different crossbar sizes. So it also shows a 95% confidence interval via the error bars. So you have your error bars over here, which denotes the sigma level that we are talking about just now. So this is 95 is 2 sigma, all right? So one can see that results are close to the ideal value of 50%. So their target is 50%, so it's very close to 50%. Furthermore, the spread of the confidence intervals is 3% at most. Okay, so when you read this kind of data, you feel 95% confidence interval, so you feel convinced the number of error is very low. Okay, and if I go back to Excel, okay, so Excel can actually give you this confidence interval. So you have the measurement just now for the metal strip. Okay, you can calculate the mode, median, the standard deviation, the mode, and also the confidence interval is 0.0016. This is at 2 sigma. Okay, clear? Clear, guys, girls?
Yes, yes, doctor.
Okay. All right, let's move on. Okay, next we move to binomial. Just now was a Gaussian distribution. Now we move to a binomial distribution. So for a binomial distribution, it describes discrete random variables that have only 2 possible outcomes, success or failure. For example, in a production quality control, you can have accept or reject. So the probability of success remains constant throughout the experiment, where n is the number of trials and r is the number of successes. These are equations used to govern the binomial distribution. Okay, let's look at an example. So this is a manufacturer of a brand of computer. So he says his computers are all reliable and that only 10% of the computers require repairs within the warranty period. So the question determine the probability that in a batch of 20 computers, 5 will require repair during the warranty period. So we use binomial distribution, and again, I go back to Excel, all right? So you have number of successes, which is 15, number of, okay, if you go back here, so the number of successes is 15, the number of trials is 20, the probability of success is 0.9, p equals to 0.9, and we choose it as false because this is probability mass function. There are exactly S number of successes, and it gives you 0.031921. So the conclusion here is that there is a fairly small chance, 3.2%, that there will be exactly 5 computers out of a batch of 20 computers requiring repair. So only 5 will require repair. Okay, so this is how you use a binomial distribution. Okay, and moving on to the next one. Poisson distribution. So we looked at Gaussian, we looked at binomial, and this is Poisson. So Poisson is used to estimate the number of random occurrences in an event in a specified interval of time or space. So these are the assumptions. So the probability of occurrence of an event in the same for any 2 intervals of the same length. The probability of occurrence of an event is independent, all right, of the occurrence of other events. So it's given by this equation over here. Okay. Let me see in my Excel. Do I have Poisson? No. Okay, so I skip Poisson. If you're interested, you can go ahead and look it up in Excel. So I've briefed you on Gaussian, on binomial, on Poisson. There are many other types of distributions which I cannot cover in my lecture. So I've given you an overview of binomial, so, and also normal, Gaussian. So Poisson you can read up on your own if you're interested. Okay, there's also students T, chi-squared, and also Weibull. You can look at all the applications for this, right here. You also have exponential, log normal, and also uniform. So all the different applications of this kind of distribution, which are commonly used in engineering. Okay. Again, do you need to use it? It depends on your experiment, on your supervisor. If they think there is no need to use, so don't need to use it. All right. So it all depends on your requirements of your experimental work. Okay. All right, so far so good?
Good, Doctor.
Okay, so we move on to statistical interpretation and summary. Okay, so this looks like it's more relevant to most of us. Okay, correlation of experimental data. Okay, so just now was just an overview if you are using Gaussian, Poisson, or binomial, right? But I think normally what we do is this. Right, correlation of experimental data using regression. That is what normally we use in IMEN. Okay, there is a coefficient. It's called correlation coefficient. It's a scatter due to random errors. It is common in all experiments. So the scatter may be so large that no trend is available. So let's look at an experiment. You have an independent variable X. It is varied systematically, and the dependent variable Y depends on the value of X. Okay, class, can you please talk? Can anyone give an interpretation of graph A, graph B, and also graph C? Hello? Hello, shall I call out names? Shall I call out names?
Yes, Doctor.
It's me.
Okay, so is someone going to talk, or shall I call out names?
Doctor, can I explain?
Yes, sure. Who's this again?
This is Purman. This is Muhammad.
Purman. Purman, I know you're very good. Does anyone else want to try? Master students, perhaps?
Maybe me, Doctor.
Yes, ma'am.
Asad?
Yes, ma'am.
Yes, Asad. Okay, we go back to the figure. What can you say about A?
A has a linear distribution.
Linear distribution.
Yeah.
Okay.
Other two have a random distribution.
Which one?
Other B and C has a random distribution. B has more random than C.
B is more random than C. Okay. All right. So that is when you look at it, you can straight away come out with the conclusion. A, you have X and Y linearly related to each other. B is a very random distribution, and C, there is some trend, but it's still random. Okay, there is some trend, but it's still random. Okay, so if the results appear as in figure 1A, we conclude that there is a strong relationship between X and Y. So in figure 1B, we conclude there is no functional relationship between Y and X. So in your experiment, don't get B, okay? Either you should get A, or in fact C is also not so good. You should be getting figure A, right? You should have some correlation. If not, you repeat experiments. However, for figure 1C, there appears to be a trend of increasing Y with increasing X, but the scatter is so great that the apparent trend might be a consequence of pure chance. Statistical parameter called correlation coefficient can be used to determine whether an apparent trend is real or not. So the question here, is there a trend or is there not a trend? This is very clear. X is linearly increasing with Y. Y is linearly increasing with X. Very clear trend. Here, there is no trend. But here, is there a trend or is there no trend? You can see that it's going upwards, but is there a trend or not? So there's something called correlation coefficient. Okay, so this is an example of example 4. So it's lap time for a race car depending on the ambient temperature. Okay, how many have been to Sepang, the race car? Nobody interested in racing.
Me.
Okay.
Ma'am, we have only motorbikes, so we're interested in racing in motorbikes.
Okay. All right. Anyway. Okay. So we have a race car and they looked at the ambient temperature. So you have this curve over here. You can see that when the temperature is increasing, so this is lap time. Lap time means how many times, how long does it take to go one round? Ya, berapa lama ambil untuk pergi satu pusingan ya? Untuk F1 circuit ya, kereta nak pusing F1 circuit, masa yang diambil melawan suhu. Lap time, masa, and ambient temperature, suhu. Okay. So so is this linear or not? Pormat, Asad, is this linear or not?
Means up to 60 it's linear. Up to 60 Fahrenheit it's linear.
And then?
And then not linear.
Okay. So if you get such a figure, what do you do? What do you do, students? If you get such a data, what do you do? Tell me, I want to hear. Pardon?
Repeat the experiment.
Okay, repeat the experiment. What else will you do?
I'll stop at 60.
That means you remove the other two data points. That's a smart way of reporting. Okay, so yeah, there are various methods, but being a researcher, you must be inquisitive. You must try to understand what is happening here actually. Why these two are giving these numbers? You're expecting it to go linear, right? So what's happening here? So you should have some inquisitive researcher mind. Okay, that's what it's, yeah. So maybe it's better to repeat, or you can use the correlation coefficient, right? Maybe if you repeat it many times and this is what occurs, so you can get this correlation coefficient. And again, you can do it in Excel as well. This is the complete calculation. So at a 95% confidence level, your alpha is 0.05. So for 6 pairs of data, Okay, so this is the correlation coefficient. So you have 6 pairs of data at alpha of 0.05, you have 0.811, the value of R. And the value that you obtain is 0.4013. So since this value is lower than RT over here, we conclude that the trend in the data is caused by pure chance. So it's not real, right? So if you repeat the experiment 10 times and you get the same results, so actually there's no, it's not real. The data is not real actually. So probably there is a limitation. Probably this trend is only valid until 60 degrees Fahrenheit. So above that, there is no trend, right? Something like that. So again, Excel can help you to do this, right? So you have what we call the correlation. So this is the ambient temperature versus the lab time, and you can get the value is 0.40153, which is lower than RT. So it's pure chance. Okay. And if you go back, okay, so least squares linear fit. So normally when you do your experimental data, you have a form of y equals to ax plus b, right? So what we do with this data is we construct a figure or a chart. We call it least squares or linear regression to fit the data. So assuming you have data pairs x and y, and for each value we have an error rate, right? So you plot. So this is a nice linear curve, right? So everything falls into place. And when you have this kind of data, normally we plug it into Excel, right? And we try to get what we call a regression line, right? So you add a trend line, okay? And you can see for this data over here, you can choose whether it's exponential, but of course, if you're choosing exponential, right? We go back here. So at the trend line, if it's linear, you can see that it doesn't match, right? If it's linear, you can see that it doesn't match with the data points. So it should be an exponential. So let me delete this. Okay, so it should be an exponential trend line. Okay, so it should be an exponential. Okay, so it fits nicely with your data. Okay, so this is a method of regression. If you look at the data point just now, okay. Okay, so there are various types of trend line options for you to have an equation, and also it gives you your confidence level, your R squared value. So the higher the R squared value, the more accurate your prediction is. So you get an equation which relates the lab time with the ambient temperature, right, which is X over here. So if you want to find what will be the lab time, for a temperature, 150 and so forth. So probably this equation can be used to determine the lab time. Okay, so this is a method of getting a regression equation for the data that you collected. Okay, so moving on. So this shows least squares best fit regression line. So this is what we call the error. How far is the actual value collected from your regression? All right, this is what we call error. And when you plus all these differences, this is what gives you your R squared value, right? This R squared value is generated from all the errors and you square them up. Okay. So you can also have a best fit. All right, but this doesn't go through the origin. You can also force it to go through the origin through 0. Some applications require for the initial value to be 0. Okay, So y equals to ax without a cut-off point in the y-axis. Okay. And variation in the data is assumed to be normally distributed and due to random causes. So in deriving ax plus b, we assume that the random variation exists in y values while x values are error-free. So do not make the mistake of, since the error is minimized in the y direction, an erroneous conclusion may be made if x is estimated based on the value for y. So you don't do a mathematical change, right? You make x as the first letter. It's wrong, right? So this is for this kind of equation, y equals to ax plus b. Linear regression of x in terms of y. It cannot be derived simply from changing. You can't make x as x equals to cy equals to d. You cannot make this kind of you cannot change it back like max, like mathematics. It's not right. That is something that you need to be careful about. Okay, let's talk about outliers. Right, so just now, for the temperature, probably you had an outlier, right? So outlier is a point with much larger deviation than other data, and you consider it as an outlier. So what do you do when you have an outlier? Just now, some said just remove that data. But as I said, being an inquisitive researcher, you should try to repeat the experiment and see whether the outlier still exists. So probably it's giving you some indication that there's some systematic error with your equipment or your measurement method, right? So don't just ignore outliers, but sometimes they can be just while you're measuring, something occurred, your attention got distracted and you collected the data wrongly. It can be that way. Okay. All right. So we looked at simple y equals to ax plus b, but you can use data transformation. Like just now, we looked at normalized frequency. So similarly, when you're doing regression, you can change your graph, not only to be y equals to ax plus c. You can use a natural logarithm, ln y. You saw that in Excel just now. You can use the log form of the data. Okay. So this is example number 5. You have pressure versus temperature, and you can see when we plot temperature versus pressure, so this is not a linear curve, right? So T over T naught equals to P over P naught to the power of n minus 1 divided by n. But when you do a natural log of the both the x and the y axis, you get a nice, beautiful linear plot. So, and you can change your equation to be ln T equals to A ln P plus B. All right, and in fact, T can, so this is the actual y equals to mx plus c of this line over here. So you get a relationship between the temperature and also the pressure, but in a natural log form. Okay, so again, data transformation. You can also have multiple and polynomial regression. So just now, the racetrack temperature versus the lab time, that was x to the power of 3, and your x can take various values, right? And in multiple regression, the best fit is considerably more difficult to be obtained. So it may not be possible to generate suitable plots. Okay. So this is another example, example 6. So you have oil mixture as a function of temperature. So you have the mass of 3 different components of the oil, which is M1, the weight, right? The mass, M1, M2, and M3. And the density, here's the density. This is not beta. What is this? What sign? What Greek sign is this? Anyone?
This is rho.
Density.
Rho. Yeah, rho. Yes, this is rho. So rho gives you the density. Okay. Yes. When you do a multiple regression in this form, which relates the mass and the temperature to the density. Okay, so you get a multiple regression equation. Okay, so when you do the multiple regression in Excel or what some other statistical software. So you can get the density of the mixture is equivalent to, you take the intercept value minus related to the temperature, this value minus, and then the second variable, which is the mass of M1, the mass of M2, and the mass of M3. So one nice equation to relate all the parameters to determine the density of the oil. So this is multiple and polynomial regression. So we looked at a simple y equals to mx plus c to multiple polynomial regression. All these can be achieved through Excel. All right, you don't need to use any complex statistical software. You can do it in Excel, but if you want to delve deeper, you want to give more meaning to your data, and if your supervisor deems it fit, use other statistical software. Some popular ones are Origin, Sigma Plot, Excel is the common one, MATLAB, Minitab, SPSS, and so forth. All right, I'm going to go through Taguchi method after this. Do you all want a break of 5 minutes?
Yes, ma'am. I think you are tired.
I'm not tired. I just want to finish the lecture. Do you need a break? Bio break? Everyone okay? Do you need
Sure,
a bio
doctor.
break? Huh? Sure. Okay, go
Continue
get
also
some
can.
water to drink.
Continue.
Continue also can. I think we take 5 minutes break. Okay, breather. Then we
Yeah.
continue back. So now it's let's see, what's the time now? 11:51. We come back at 11:56. Okay, bio break. Okay, let me settle some WhatsApp. Okay, 11:56. We come back here. Okay.
Doctor, are you there?
Okay, let's.
Doctor is not.
Okay. All right. Okay, shall we continue?
Yeah.
Okay.
Yes.
Okay. Can all of you see my slides?
Yes,
Yeah.
ma'am.
Yes, doctor.
Yes.
Okay. All right. So 2 weeks ago, Dr. Anik taught all of you how to use Minitab for factorial design and also for fractional factorial design. He also touched on response surface methodology, RSM. So today I will cover Taguchi method. Okay. So okay, I told all of you to download the trial version, but I also downloaded it. But this morning I just realized that some of the examples are, you cannot use the examples. Am I right?
Demo for the high-speed camera.
Pardon?
Down there,
Uh-huh.
demo for high-speed camera. I know. I think you need to use right. Last time. So,
Okay. I'll just move on. Okay. So this is a paper from Scientific Reports. Okay, so if you look at this paper, it's about the optimization of double diffusive mixed convection in a BFS channel filled with alumina nanoparticles using Taguchi method and utility concept. So basically this is a channel. It's called a BFS channel, backward facing step channel. So you have an inlet and also an outlet, and it's filled with alumina nanoparticles. So what the researchers are trying to do is they're trying to optimize this channel. And if you see here, they have used Taguchi method, L27 orthogonal array, and they have 6 factors. All right, what are the factors? The first, if you look at the factors, is related to their cause and effect diagram, which we call the fishbone diagram. Basically, there are 3 parameters, which is the channel geometry, the flow parameters, and also the nanofluid. So this is the channel geometry, the height, the width, and so forth. The flow parameters, because you have gas or liquid or whatever flowing through, so we call it the flow parameters. And you also have nanofluids inside the chamber. And what are the parameters affecting these 3 main parameters? You have expansion ratio, you have the Reynolds number, RE, you have the buoyancy rate or ratio, and GR is actually the thermal Grotov number. All right, so these are just the technical Grasov number. These are the technical terms related to the channel. Okay. And in terms of the nanofluid, what are the factors affecting the nanofluid? The viscosity, okay, the volume fraction, the shape of the nanoparticle, and also the thermal conductivity. And what is the output expected from this experiment? So the researchers are trying to look at the heat transfer, the mass transfer, and the wall shear stress, 3 main outputs. So they got hold of 6 control variables. So they did not take all. So in terms of the channel geometry, they looked at the expansion ratio and they labeled it as factor A. And then in terms of the flow parameters, they took all 3. The Reynolds number is factor B. N is the buoyancy ratio. And this thermal Grasov number is factor F. In terms of the nanofluid, they looked at the nanoparticle volume fraction, which is over here, and also they looked at the shape of the nanoparticle. So they did not take into account these 2 factors. Why? So probably this might have been experiment number 10. So from experiment 1 to experiment 9, they have determined that these 2 factors may not be significant, and they have removed it from their final experimental. I'm just assuming, okay, that is the reason why they have removed these 2. So similarly, in your master's and your PhD journal, PhD studies, if you are trying to use statistical methods, it is good to have what are the parameters affecting your, you need to know what are the factors affecting your experimental work. And what are your output parameters? We call this as figure of merits, right? Whether you're looking at voltage, variance, frequency, optical intensity, all this is what we call figure of merit or the response or the output. So you need to know what is the input parameter and what is the output parameter. So else than knowing the input parameters, you need to know what affects the input parameter. So you can ask me, doctor, what if I have so many like this, right? So if you have many parameters, you need to find out what is giving a significant effect on the output. So that is where methods such as fractional factorial design or factorial design or Taguchi method can help you to determine what gives an impact to your output parameter. Okay. So in this case, the researchers use signal to noise ratio, SNR, of larger the better for two responses. So they want a larger heat transfer and a larger mass transfer, but they want to reduce the stress. So they use the SNR of smaller the better. So my message to you is, if you think that statistical methods are not crucial for your experimental work, that is fine. But bear in mind that they can also help to give better meaning to your results, and such that you can publish in high impact factor, provided that your statistical analysis is accurate and meaningful for the research community. So this is one example that I plugged out for you. Okay, so if you want to know in detail, you can go to this link over here. Okay, and they also looked at the signal to noise ratio and the effect on each parameter using Taguchi method, right? So you can see that there are three levels. They looked at three different levels. So as is similar to fractional factorial design and also factorial design. If the SNR ratio is higher, that is a better level value. For here, you take this value over here. For the Reynolds number, you take this value over here, and so forth. You take all the higher values and you get a optimized parameter for all the six factors, which can give you a high heat transfer, high mass transfer, and low wall shear stress. Okay, so this is how Taguchi method is useful. Okay, so this shows the ANOVA. So later when we look at some examples, you can also see how this ANOVA is developed. Okay, so just one example of a Taguchi method in a journal publication. Okay, so Taguchi method originated in Japan, okay, and in USA. So just some history. So in India and Malaysia, it's more than 350 case studies in the last 20 years. So this is Genichi Taguchi from his book, Taguchi's Quality Engineering Handbook. So I have this book, Quality Engineering Using Robust Design by Madhav Patke, and my guru or my teacher for Taguchi method is Prof. Apte. He's from IIT Bombay. And I've been learning Taguchi method from him for the past 10 years. Okay, so he's a regular instructor. And I think some of you have in fact taken his course early this year before COVID hit Malaysia. So in January, we had a short course on Taguchi method. So Prof. Apte was the one who briefed all of us. And whatever slides that I'm showing you, some are from him and some are from myself over the years after being coached. Okay. Okay, so this is the same slide. Okay, so conventionally, you vary parameters in a controlled manner, one at a time. So this is a full factorial design. So what is the disadvantage? You have a series of experiments and you may end up with a negative result. Okay, and you have design of experiments. So this was introduced by Ronald Fisher late in 1930s. So it was used in agriculture. So it's less than factorial experiments. You use analysis of variance, okay, ANOVA, and you look at factor effects and also interactions, how one factor gets affected by another factor, and also the interaction between them. Okay. All right, Taguchi method is aimed at reducing variance in the output. Remember your sigma, 1 sigma, 2 sigma, 3 sigma, and so forth. We want to reduce the variance. We want a nice thin Gaussian curve. We don't want bulky Gaussian curve, while allowing variations in the input. Okay, by changing the input, you still get a nice thin curve, reduce the variance, making the process of product robust. So orthogonal arrays, it can be controlled with 2 or 3 levels. For example, if you have temperature, you have low temperature, medium temperature, and also high temperature. We call them levels. And here we have L8, which means you run 8 experiments. So these are for 7 control factors, right? The input parameter is 7. And each of these parameters have 2 levels, one low level, one high level. And if you are running a full factorial design, this is 128 experiments. Versus Taguchi method, you only need to run 8 experiments. So you can see the difference in the number of experiments that you need to run. Similarly, for L9, you have 4 control factors with 3 levels each. So one low temperature, medium temperature, and high temperature. So here maybe it's just low and high temperature. And if you're running a full factorial, it's going to be 81. 3 factors for 3 levels for 4 control factors, so it's 81. And in Taguchi method, it's just 9 experiments. Similarly, L18, where you have 1 control factor with 2 levels and 7 control factor with 3 levels. You can also mix and match this. So full factorial, you're going to have 4374. And all control factors are supposed to be orthogonal. Okay, and hence,
Doctor?
yes.
Doctor,
Yes.
excuse me to
Yes.
interrupt you. Can I ask you something?
Yeah, sure, please.
The 2 to the power of 7, that is the 7 factor, right? So which mean for if you use the Taguchi method will be L8, is it?
Yes, 8 experiments.
So same goes to if you have a 3 to the power of 4, you use the Taguchi method level 9.
Yes, correct.
So you have kind of like a table, is it? When you have
Yes,
this
you have a fixed table, Siva. You have a fixed
Oh,
table. You just have to
okay.
follow. You have to follow the table set out by Genichi Taguchi. You have to use his table.
Understood, Doctor. Thank you.
Okay. All right. So this is the properties of. So this is L8. Okay, where you can see this is A and B. So any 2 columns have all combinations equal number of times. So A2, B2 occurs 2 times. A1, B1 2 times, A1, B2, A2, B1, A2, and so forth. So C1, E1, C1, E1 2 times, C1, E2 2 times, C2, E1 2 times, C2, E2 2 times. So similarly, C1 and E1, so they all occur 2 times. So balance for each factor level, A1 occurs 4 times, A2 occurs 4 times, D1 occurs 4 times, D2 occurs 4 times. Okay. So this table is fixed. So it's balanced for any other factor. This table is fixed. You cannot change it. Okay, it's fixed. It's fixed by Genichi Taguchi. You just use it to run your experiment. That means if you're running the first experiment, you need to follow this sequence. If you're running the second experiment, you must follow this sequence. All right, so that is the properties of L8. And for L9, so you have 4 factors. And any 2 columns have all combinations equal number of times. Okay, so A1, B2. So we call it a magic square. It was developed by Genichi Taguchi, and it's a magic square. By following these sequences in the experiment, you can get a significant signal to noise ratio, as we'll see after this for a few experiments. Okay, so experiment 1, you must use A1, B1, C1, D1, okay, and so forth. So 1 to 9 has got fixed number of levels that you need to follow. So these are giving the reasons. What do you mean by orthogonality? So each factor and the levels, they occur the same number of times. So it is balanced for any other factor. Okay, so that is what it means by orthogonal array. Okay. Okay, so this I showed you L8 and L9. It is similar for L18, L27, L81 is similar. All right, so they are orthogonal. Okay, so this is L9 experiment with 2 noise factors. Okay, so you have factor A, factor B, factor C, and factor D. And as you can see, this table here is fixed. When you're running experiment number 1, you must use A1, B1, C1, D1. If you're running experiment 2, you must run A1, B2, C2, D2. All right, these squares are fixed. And you can include noise in Taguchi method. So you have E1 and F1, and again, you can vary them to look into all possible causes of noises.
Doctor, sorry
Yes.
to interrupt. Just want to check, A111 is actually the lower spec value, is it?
Correct. If you remember from the paper just now,
The
right?
level, right? The level.
Yeah, the level.
The level 3.
Correct.
Right, I got it, doctor. Got it.
Yeah. So if you see, this is the level, right? You
Right.
choose 3 levels or 2 levels. So
Understood.
it's referring to lower level, mid level, or higher level.
Oh, so the middle level will be 2.
It depends on your experiment, right?
Yeah,
It
depends,
depends
yeah.
on your experiment. What is normally a common good practice is if you're having if you want to use 2 levels, you use a low value and a high value. Sometimes some of your equipments, they have a lower limit and a higher limit, right?
Yes.
So you can use that as a lower value and a higher value. Or if you have five values, you can use a lower value, a mid value, and a higher value.
Yeah, understood.
Yeah. Okay. Okay. Bear with me. Okay. So all right. Okay. What is the aim of Taguchi method, and in fact all statistical methods? The first is we want to, so you start with the initial measurement, okay, and the first thing that you want to do is reduce your variation. You try to make the Gaussian curve smaller, right? You reduce your sigma, try to reduce the variation, and the second thing that you try to do is you bring your mean on the target. If this is your mean, or if this bigger mean is your target value, you try to bring it to, we call it bring the mean on target. Okay, so 2 things that you want to do. The first is reduce the variance. The second is bring the mean on target. Okay. So causes of variation, or what we call the noise factors. So if you are using unit to unit variations, this can be raw materials, manufacturing equipment, or workmanship. Operating conditions, it can be temperature, humidity, dust, supply voltage, things that you cannot control. Vibrations, human error, heavy duty loading, light duty loading, and in terms of deterioration, components and also consumables. So noise factors can be quite tricky because you need to correctly identify, you need to differentiate between factors and also noise. All right, what you can control and what you cannot control. So more often than not, it's temperature or humidity, but are you taking the correct noise temperature or not? Or are you taking the correct noise factor or not? So these are things that you need to ask yourself before you want to embark on a Taguchi experiment. Okay, and these are more effects of variations during manufacture, during the customer use, and also with deterioration with time. Okay, so these are all common noise factors in an industry-based area. Okay, so this is the P diagram for what we call static problems. So in static problems, you have control factors, your input parameters, and then you have noise factors. You have temperature, humidity, and so forth. And then you look at the output. All right, for example, you want to look at the heat or the mass or the shear stress and so forth, the output. We also have what we call the dynamic problem. So you have a control factor, you have noise factors, you also have signals coming in. What are examples of signals? For example, in my case, I have for plasmonic sensing, I have control factors, the wavelength, the thickness of the material, and then the noise is the temperature. For signal, I have refractive index values of the analyte. right? So these are signal values, and I look at the response curve, or what we call the sensitivity of the sensor. That is my output.
Doctor, how do you differentiate between signal and control factor? I don't know what is signal.
Signal is like you want to look at variability into your system, right? Control factors are like things that you vary. Actually, signal is actually related to the output, something that you change in the output, right? Like my example just now, like it's a plasmonic sensor. So my output is sensitivity, but the sensitivity is determined by the refractive index of different analytes. So those different refractive index, they are not a control factor, but actually they are a signal because they give an impact to the to the output. All right. The control factors are the thickness of the material, the wavelength, things that I set. And the signal factors are linked to the output. That means if you change the signal factors, so it's kind of tricky because actually all these three are kind of tricky because you need to identify them correctly actually. You know, so
can I say the signal is not considered as the control factor for that
yes,
particular experiment?
yes, it's not the control factor. It's
All
not
right, all right.
yeah, it's not a fixed value actually. But it's not a noise. It's not something that you cannot control actually. You just want to see if you change like the analyte refractive index, what is the impact to the output, right? So we call this as a dynamic problem. Okay, you can look up for Minitab. You can look up for, there are many examples given in the Minitab website for different kinds of dynamic problems, right? But commonly we just use static problems, right? And recently I have one student who have used the dynamic problem for her work as well. So it's very interesting. Of course, the number of experiment increases because you need to look at all the signal values, but it gives some very interesting results for us. Okay, so as I mentioned, step one, when you're using a robust design, first you need to reduce the variation. So this is your starting data. Okay, so step one, you make it thin, reduce your variation, your mu, right? Reduce it. And step two, you adjust the performance on target, leaving the variation undisturbed. Then you move it to the mean value. Okay, so when you do a variation reduction, this is equivalent to looking at the signal to noise ratio, larger the better, or smaller the better, or nominal the best. And when you are doing the mean on target, we look at SNR effect on the mean. All right. Later, when you do a Minitab, you can see two types of SNR. One is the output SNR, which is larger the better, smaller the better, or nominal the best. The other SNR is SNR of the mean, to bring the mean on target. So reduce the variation, make it thin, then bring it on target, okay, to the mean value. So two-step optimization. So what are the steps in Taguchi method? The first is you need to know what is your main function. What is your output? Are you going to look at frequency? Are you going to look at output power? Are you going to look at wavelength? You need to know your experiments, okay? The side effects and also the failure mode. You need to identify the noise factors, the testing condition, the quality characteristics. Identify the objective function, what signal to noise ratio you need to use. That means, do you want your output to be larger? Of course, if you're looking at output power, for example, if you're designing a laser or LED, of course you want the output power to be large. So you choose objective function, signal to noise ratio, larger the better. Okay. Suppose you are designing a photodiode and you are trying to reduce the leakage current. All right, leakage current is not good for devices, so you want it to be small. In fact, you want it to be 0. So then your objective function will be smaller the better. The output current should be smaller, the better. Okay. Suppose I'm designing a MOSFET, right? A transistor. A silicon transistor, the threshold current should be at 0.7, right? Silicon base. So then I have a nominal value. I need to meet the 0.7, right? And so I have nominal the best. I have a particular value that I need to meet. So it becomes objective function, signal to noise ratio, nominal the best. Okay. So you identify the objective function to be optimized. You identify the control factors and also their levels. And then you select the orthogonal array, then you conduct the matrix experiment, then you analyze the data, you predict the optimal levels and the performance, and then you perform the verification experiment and you plan the future action. Okay, so we will look at two examples, spark erosion machining and Smith trigger circuit design, and the third one is from my own work. It's weak cell optimization, and the last one is actually given by Minitab, but I just realized that you can't get the example from the trial version, but I'll show you from my older version of Minitab on how you can get this golf ball optimization. Okay, so this is a spark erosion machining. All right, you have a tool. This is the spark erosion tool. It is an electrode, and it is drilling into a metal job or a metal substrate. Okay, and the first step, identify the main function, the side effects, and the failure mode. So the main function is we want to optimize and stabilize the EDM performance, the drilling machining of the performance, where we have two output. One is the material removal rate, and the second is the percent electrode wear. You see, when it's drilling, two things happen here. The material gets removed and the electrode also gets weared out, right? Dia terhakis, ya. So dua benda terhakis, electrode pun terhakis, logam ni pun terhakis. But so since the first trial application, no other quality characteristics will be observed. So this is first time they're doing this, right? So normally in experiments, you have round 1, round 2, round 3, and then you become, you kind of, you know what parameters are important for your output, right? Then you can refine your experiments, right? And the failure mode, the control factor levels are selected so that there will not be any failure during experimentation leading to aborting an experiment. I'll explain this further in my laser experiment, because in laser, your thickness should be chosen such a way that it can lace. If you choose a wrong thickness, the laser won't lace because you do not have oscillation occurring. So in Taguchi method, you need to make sure the levels that you are choosing still enables your output parameter to be obtained. Okay, then only it makes sense to run the experiment. Okay. So back to the spark erosion machining. So material removal rate. All right, it is too late when you are drilling into the electrode. You want the removal rate to be increased. You want it to drill faster. So you want the material to be removed faster. So that the problem is it's too low. All right, so your output is to increase it. That is your aim. That is your objective. You want to increase it. And the electrode, the driller, right, the drill, you do not want it to reduce, you do not want it to wear out, terhakis dengan cepat, the percentage, yeah. So it's too high. These are the problems of the experiment. So the aim is to increase the material removal rate and also to reduce the electrode wear. So you have two parameters or two output parameters. What are the control factors? The pulse on time, all right, the pulse which goes through the electrode, the gap current which goes through the electrode, and also the bipulse current. So you have three control factors. Noise factors are the material hardness. You cannot control the material hardness. When you purchase the material, you cannot control the hardness. And the second thing is the temperature. These two things are out of your control. So we take them as noise factors. The testing conditions. So to capture the effects of the noise. So you can see here for the hardness, there is a low hardness H1 and there is a large hardness H2. So H1, H2, low and high levels Of course, these are within the limit of the material. When you're purchasing, you have a spec. You can take the low level and the high level. And then there's temperature, low and high bath temperatures. So these are the noise factors, H1, T1 and H2, T2, right? And also the in-betweens. Okay. Next is identify the noise factors, the testing condition, and also the quality characteristics. So you looked at variation in hardness of material, variation in dielectric bath temperature, hardness and temperature, H and T. So the testing condition, you keep the sparking time constant for all experiments. You don't change the sparking time. So the noise capturing test conditions, for each experiment, you make 4 workpieces under the following noise conditions. So when you run experiment 1, right, for L9, okay, or actually it's in the next slide. Okay, when you're running, when you're running L1, L2, L3, you need to run for the noise factors as well. Okay, so this is the way that you run the noise. You need to repeat each experiment. Just now you saw there were 9 experiments, so you need to run it for all the 4 different noise factors. So H1, hard, room temperature and high temperature, H1T1, H1T2 or H2T1, H1T1, T2 and H2T2. Okay, so 4 different noise are captured. Identify the objective function. So Taguchi method is based on signal to noise ratio. So you have 4 different signal to noise ratios. You have larger the better depending on your output. Do you want your output to be larger? Or do you want your output to be smaller? Or do you want nominal output? So for material removal rate, of course you want it to drill more. You want more material to be removed. So we use larger the better. And for electrode wear, you do not want the drill to wear out so fast. So you say electrode wear percentage, smaller the better. So 2 different objective function. So it's given by this SNR ratio. Okay, so basically you can see that the difference is the output is divided by the output, and over here it's taking the total summation of the output parameters. Okay, so the difference in larger the better and smaller the better. Identify the control factors. So we have 3 control factors: pulse on time measured in microseconds, gap current in amps, and also the bipulse current also in amps. And 3 levels are chosen. Now, what if I have 5 levels? What if I have 10 levels? So as I mentioned earlier, you need to choose such a way that you have a lower level, a higher level, and a medium level. So this is the way to do it, even if you have 5 temperatures or 10 temperatures. So try to divide it so that you have 3, and then later you can refine. You can do the 2nd round, 3rd round, and so forth, and refine it accordingly. Okay. So the numbers which are underlined are actually the initial value. So initially it was 200, initially it was 34 amps, and initially it was 3 amps. So if you look at the orthogonal array matrix experiment, so the degrees of freedom, I think all this is covered by Dr. Anik's lecture. So if you have forgotten what is degrees of freedom, please go back and look at Dr. Anik's lecture notes, degrees of freedom. So 1 for mean and 2 each for 3 factors. All right. So giving you 7 degrees of freedom. And the orthogonal array for 3 level factors. Okay, you have L9, L18 or L27. You have 3 options, but we choose L9 because we have 3 factors and 3 level factors. Okay, so we choose L9. And this is the orthogonal array. As you can see, this is fixed. All right, this is fixed. You do not change it. When you run experiment 1, this is what you need to follow. Experiment 2, this is what. Since we do not have a 4th factor, we leave it blank. Okay. Conduct the 9 experiments of L9 array. In each experiment, measure the material removal rate and also the percentage of electrode wear for all the 4 noise conditions of hardness and also the bath temperature. For example, you have experiment 1, you put 150, 30, 0. So this is empty. and then you look at what is the material removal rate and what is the electrode wear. Okay, so these are the values obtained. This is the SN ratio. All right. So you look, this is the output parameter. Okay, Y. Y over here, 1 over Y, you sum it from 1 until the number of N, the number of samples, 1 over N. Of course, this can be done in Minitab and also in Excel as well. So these are the SNR values. Okay, these are the SNR, signal to noise ratio, and it is given in dB, decibel. So for both the MRR and also the electrode wear. And you analyze the data, you predict the optimum levels and also the performance. So let's look at the data. So this is for the A1, which is the pulse on time, B is the gap current, and C is the bi-pulse current. So as you can see here, it shows that, so in Taguchi method, the larger the SNR value, the better is that level. So this is for material removal rate. It shows that A2, B3 and C3 gives the best MRR value or the output. Okay. In terms of the percentage of the electrode wear, it is A3, B1 and C3. Okay. Factor effect, so it's the same. It's just a summary of both in one page. And so we started with A2, B2 and C2, and now the optimum is A3, B3 and C2. And this is for MRR and this is for electrode wear. So they both gave similar values, and you can see here the predicted is 39%, but in actual when you run this experiment, you get a 3-to-1 material removal rate. And your percentage of electrode wear is 1.7. So as you can see, the electrode wear has reduced and your material removal rate has increased. So the increment is 36%, the reduction is 57%. Okay, so the results match with the prediction, so you can adopt the new settings. So initially you're using A2, B2, C2, now you can use A3, B3, C2 with increased material removal rate and reduction in the electrode wear. Okay. Hello. Hello.
Yes, ma'am.
Okay, Doctor.
Can all of you understand how it works? It's similar to factorial design. It's similar to that. Only thing you have the function, signal to noise ratio. Okay. All right, I'll move on. Okay, I'm sorry, we are a bit ahead of time, 12:33, 3 minutes ahead. I think I need another 10 minutes to finish up the slides. Okay, so the next one is a circuit design. Okay, and what we are trying to do is we are trying to get insensitivity to temperature. All right, so this is a Schmidt trigger circuit. So if you see here, there are some resistive resistor values, and also we have some diodes here with a gain, and we are trying to see how can we optimize this circuit so that we can reduce the dependability on the temperature for this particular circuit. Okay, so a typical Schmidt trigger circuit, it gives low trigger voltage and VLOW and upper trigger voltage, and we need to design a circuit which gives very low temperature sensitivity to temperature variation between 0 and 100. That means when you vary the temperature, whether you're staying in the Arctic or you're staying in Malaysia, a very cold place or a very hot place, your trigger voltage does not change, right? So it's insensitive to temperature change. The circuit behaves the same. And adjust the low threshold trigger voltage to 3. So we want to change, or we want to achieve V low to 3 volts. Okay, so two things we're trying to achieve. Okay, so these are the control factors. So these are resistor values for R1 and R2. So this is R1 and R2, the resistor values. And beta 1 and beta 2 is actually the gain, all right, for these two diodes. Okay. And so you can see here, different temperatures are used from 0 until 100. So these are the noise factors. So when you run experiment 1, you have to use these variations in temperature. That means you have to run at 0, you have to run at 25, 50, 75, 100. Done, experiment 1. Experiment 2, you run using these values at 0, 25, 50, 75, and 100, and so forth, and then you complete all the 9 experiments for different varying temperatures. Okay, so this is with one noise factor. Okay, so this is actually a circuit simulation using PSpice. It's a PSpice simulator, and all 5 different values of temperature were used. So you have 9 groups of data. Okay, now we want to find nominal the best. Why? Because we have set the voltage as 3 volts, right? It's a value that we want to achieve for the circuit, so it's nominal the best. So we plot V out versus V in to show the trigger voltage at different temperatures. Okay, so as you can see here, it is this is the worst case scenario. You can see that the trigger voltage changes with temperature. Okay, so this denotes this is the input ramp of the voltage. So this is the trigger voltage at different temperatures, right? So it differs. If you see just now, the trigger voltage differs from 3 volts, it goes higher and higher as the temperature increases. So it's not sensitive to temperature changes. But now upon optimizing it, you can see that the trigger voltage stays at 3 volts even though the temperature changes, whether you're in the Arctic or you're in Malaysia or you're wherever you are, right? The trigger voltage remains the same at 3 volts. Okay, so this shows the factor effect plots for signal to noise ratio for the resistor values and also for the gain. This is for nominal the best, and this is for the mean. Just now was a signal to noise ratio for nominal the best. This is signal to noise ratio for the mean. Okay, and as you can see here, there is no effect on beta 1 and beta 2. It's pooled. There is no effect in the changes of the gain here, right? So we plot V out versus V in, then we find the dominant factors and their levels, and we predict the best results, and then we get that. It's very similar to factorial design from here onwards. Okay, and so you have the nominal the best and also the mean. So the dominant factors, as you can see, is R1, beta 2, right? And the optimum settings, it can be A1 or A2, right? It can be these two, either one. And for R1, it's either 220 kilo ohm or 470 kilo ohm. These are the level values. And for B2 or beta 2, it is the second level, which is 300. Okay, the gain value. Okay. So for adjustment purposes, remember this is to decrease the variance and this is to bring the mean on target. Remember your Gaussian curve, the first is you want to reduce the variation. The second is you want to bring the mean on target. When you want to bring the mean on target, you look at signal to noise ratio for the mean. So you need to adjust R2 from 220K to 1 mega ohm, right? This value gives you the best, this would bring your mean on target. Okay, so then you run confirmation simulations and results based on the prediction. So, so in conclusion, it is the only method that encourages noisy inputs during experimentation. So it produces robust processes and products. Okay. So you use the adjustment parameter R2 to adjust the Smith trigger voltage to the desired value of 3 volts. Okay. So moving on. So a product delivers target performance each time the product is used under all intended operating conditions and throughout the product's intended life with no harm to society. This was defined by Genichi Taguchi way back in 1930s when he first introduced a Taguchi method. Okay, so this is my own work, case study number 3. Okay, so this is on a long wavelength vertical cavity surface emitting laser. So basically this is a DBR laser. You have a top mirror, distributed Bragg reflector mirror, and bottom distributed Bragg reflector mirror. These are all the layers inside this device. And what I looked at is larger the better for the peak lasing wavelength, because I wanted a longer wavelength. And for the this is the peak lasing power, right? This is a typo. This is peak lasing power. You want a larger output power. And for the wavelength, I want it to be a fixed wavelength, which is 1.55 micrometers or 1550 nanometer. So I had 4 control factors, which is the multi-quantum well quantity, the multi-quantum well thickness. So this is the component, the mole fraction in the material which is used as the active material, and also the dopant concentration. So in terms of noise factors, since it is using CVD method, it's very hard to control the pillar width and also the device width. It is out of control sometimes. And so these are the nominal values, initial values. So 4 control factors, 3 levels, 2 noise factors at 3 levels. Okay, so this is the peak lasing power and this is the peak lasing wavelength. So this is using SNR larger, the better. Using SNR nominal, the best. Okay. So as you can see, for the lasing, there are some zero values here, because in lasers, what's happening is when you do not choose your layer thickness correctly, the laser does not lase. So after this, the whole thing was repeated again with the L4. Okay, and just using what values work. So if you summarize, so using larger the better for the peak lasing power. So this is the initial level, this is the predicted level, and after the predicted level was run again, from initial lasing power of 4.84, it increased until 9.51, which is a 96.5% improvement. Okay, so this shows you a method of how Taguchi method can be used to optimize your output parameters. Okay. Case study number 4 is actually from Minitab. So this is actually to analyze, this is a static design, by the way. So you have 2 parameters here that they want to look at. One is the golf ball and the second one is the golf club. So this is actually a golf ball manufacturer. Okay, he's a manufacturer of the golf ball, and they want to optimize the golf ball such that they want to look at the core material, the core diameter, the number of dimples, you know, the dots on top of here, and also the cover thickness. And they want the ball to have, what is their output parameter? They want it, they want to look at the flight distance. Of course, larger the better, right? You want your golf ball to go far, right? So the engineer measures the flight distance for each club type. Okay, so this manufacturer, he produces the golf ball. Of course, the golf players, they bring their own clubs, right? Their own stick, golf stick. So some of the golf clubs can be a driver or a 5-iron. And the golf ball manufacturer wants it to be a noise factor. So whether the golf player is using a driver or a 5-iron, the golf ball must be able to travel very far. It must have a good large flight distance. Okay, so if you open this in Minitab, okay, I'll go ahead and do it in my version 14. Okay, so, all right. Okay, so this is Minitab version 14. Your trial version, if you downloaded the version 19, it does not work actually. So I'm going to open worksheet. Okay, so if any of you want to get this Minitab version 14, it's a bit old, but it still works. You can come and see me and I'll be happy to give it to you. So golf ball. Okay, so we open it. Okay, so okay, what did they look at? Okay, in terms of material, there are 2 types of material, liquid and also tungsten for the golf ball. Diameter, there is a 118 and also 156, 2 levels. Dimples, also 2 levels, 392 and also 422. Thickness, also 2 levels, 0.03 and 0.06. And remember, the noise was the driver club type and also the iron club type. So these are the output parameters of the distance traveled by the golf ball. So this is using L8. Okay. And now if you go back to my slides, you can just follow. You can just analyze the Taguchi design, the driver and also the iron. Okay. So it's similar to what Dr. Anik has taught you before this. You go to ANOVA or rather DOE, and then you go to Taguchi, then you analyze the Taguchi design. So this is the response data. Okay. And then for graphs, we look at signal to noise ratios and also the means, and then we want them to display the interaction plot. Analysis, signal to noise ratio and also the means, terms. Okay. So else than looking at the individual parameter, we also want to look at the interaction of the material with the diameter. The manufacturer wants to look at the interaction between these two parameters, so he included A, B as well. Okay. And then options. Okay, you choose larger the better because you want the ball to travel far, right? Larger the better. Larger is better. So you can see here you have larger the better, smaller the better, and nominal is best. And if you see here for nominal the best, there's minus and also there's plus. So this is depending on your output value, right? If it's because it's using a SNR, so depending if your value is very small, after you log it, it becomes minus, right? And then if you log it, then it can also become positive value. So depending on which value you're going to use, right? Okay. And let's click on OK. So it generates, okay. So similar to what Dr. Anik has briefed you 2 weeks ago, you have your main effects plot. So as you can see, the SNR of liquid gives a higher SNR value, diameter 118 higher value, dimples with 392 is higher value of SNR, and thickness is 0. But this is for the means. Let's look at for the SN ratio. So this is the interaction plot. This is the main effects plot. Okay. So so same A1, B1, C1, and D2. Okay. And in terms of interaction, how does the liquid and also the material interact? You can see when you're using a liquid ball or liquid material, the SNR is higher for liquid, right, versus tungsten. Right, am I right? Or diameter. This is for diameter and this is for the material. So, so what's the summary of this? Let me go back to my slides. Okay. So these are the output parameters. So you can look at the signal to noise ratio. So this is calculated by Minitab. And it's important to look at the R-squared values, the error values, to make sure that they are near to 100 so that you minimize your number of errors. Okay, and also there's an interaction parameter over here. So this is for the means, just now for the SNR ratio, larger the better. And so you can see here, this gives you the response table for these SNR ratios and also for the means. And what is the summary? We can say that to get a golf ball with a higher flight distance, you need to use liquid core. You need to use core diameter of 118, dimples of 392, and cover thickness of 0.06. If you use these parameters, your golf ball will give you a large distance, irrespective of what golf stick that you are using. Okay. Okay, I think that's it for my class. I'll just summarize what we have gone through for 2 hours, 2.5 hours, 2 hours and 20 minutes. So I shared with you data collection, 10 commandments, some common statistical terms that, and then usage of Excel for simple statistics and also regression. And we looked at a few case studies for Taguchi method, and also usage of Minitab for further statistical analysis. Okay, so these are some books that were used. Most of my material came from all these books. Okay, and if you're interested, you can get it from me. I also have those books with me. Thank you very much for being patient with my lecture and for paying attention. Thank you so much. So if you have any questions, I'll be happy to answer them for you. Hello? All sleeping already? Hello? Hello?
Yes, Doctor.
Okay, is it clear? Are all of you clear about Taguchi method? How do you use it? How do you run it? Are all of you clear? Clear or not clear? Or you don't understand?
50-50.
50-50.
Kind of clear. Not sure.
Little bit,
Okay.
madam.
The thing about Taguchi method is until you you run it, it's very hard to understand it. So that is my personal experience. So even over the years, I've been using it like for 10 years. So even until today, it's still a trial and error, you know, especially in choosing your control factors. You learn new things when you use this set of control parameters and these levels, you get this set of data, and then you tweak and you refine. So it's a learning process. So I don't expect you to understand fully, but once you start using it, then you'll appreciate how it's useful for your experimental work. Okay, so feel free to drop by in my office or email me, or in fact you can call me if you want to know further. And I hope next year or the year after, once COVID is free, we can get Prof. Apte back here to guide all of us again in using Taguchi method. Okay?
Okay.
Okay, madam.
Okay, Doctor.
All right.
Okay, Doctor.
So my class is over, but evening what you can do is you can try to use Taguchi method. You can just Google from Minitab examples, and you can try to use the dynamic version as well and try to understand Taguchi method. Okay. All right, class.
Okay, doctor.
Okay.
Thank you so
Okay,
much. Right.
Thank you,
Okay.
Doctor.
Okay. Bye bye.
Thank you.
Bye.
Bye bye.
Thank you so
Bye bye.